Okay, bell work today. Students spent 10 minutes working on the previous test. We will score that, go over their answers, and they'll get a point for everyone that's correct. Text, they're introducing elements here, and you see on the next page where they have Mendeleev's first periodic table. One of the most difficult things to organize the elements concern the neutron, and the neutrons are associated with isotopes, right? And we talked earlier in the year about how carbon has isotopes. So you've got like carbon 12, you've got carbon 13, and you've got carbon 14. And we talked how carbon 14 has a half-life of how many years? You see that up on the board? It's got a carbon half-life of around 570 or 5,730 years. So carbon 14's half-life is 5,730 years. So what's the half-life of carbon 12? Anybody know? Raise your hand. Now, when you hear this, you're going to think to yourself, okay, carbon 14 has a half-life. Well, then carbon 12 and carbon 13 must have a half-life as well. Because you learn in school that carbon 14 is 5,730 years. So you're thinking, okay, well, I heard in biology that every carbon atom in my body was created in a star. So carbon 12 is very stable. It does not decay into carbon 13. So a lot of people they learn in life, there's stages to life. You have like little life, midlife, and old life. So most people, when they hear carbon 14, they're like, okay, so that's the older stage in life. It has 5,000 years. But carbon doesn't work like that. Carbon 14 is not formed from carbon 13. Carbon 14 is formed from nitrogen. It's called a nitrogen-carbon cycle. So it's kind of separate from carbon 13 and carbon 14. That is. Carbon 14 is separate from carbon 12 and carbon 13. It's got its own little cycle going on with nitrogen. So if you wanted to keep carbon 12 stable throughout the entire universe forever, what would you put it in? Ever seen a commercial on TV? A blank is forever? Raise your hand. Starts with a D. Yeah, a diamond is forever. The diamond structure prevents carbon from being bombarded with like neutrons and other particles. So it's a very stable structure. That's why a lot of people like diamonds, because they have this mystique to them, like they're going to last forever. Now, in the universe, diamond floating around, it could go into a sun or, if you take a diamond, you heat it up and drop it in liquid oxygen, it will burn. Carbon can react with other things and form other elements. Carbon isn't, isolated by itself. It just doesn't have a predictable pattern to do this. So all carbon does not follow a particular pattern to form another element. Is everybody clear? So it's considered to be very stable. You can look at patterns, and when you go on the internet and you look at the isotopes of carbon, it will say carbon 12, 99% of abundance, and it'll say stable next to it, because it's not going to follow pattern to decay into something else.
That are based on differences in the physical properties of the substance. For instance, a mixture of iron and sand can be separated into its components with a magnet, because a magnet will attract iron but not sand. Numerous techniques have been developed that take advantage of different physical properties in order to separate various mixtures.
Have our tests and the answers. Work. We're going to retake our tests. We're going to spend about 10 minutes on this, because it's kind of like when you play a sport, you practice one concept more than once. So we're basically seeing from Friday, do you remember some of the questions that you took on the test Friday? So you're going to get out a separate piece of paper, and then I'm going to pass back to you the scantrons here in just a second, and we'll go over the answers, and you'll get a bell work point for each one you answer correctly. So it's just another way of reinforcing the topic. And then at the end of the period, I'll collect this, or correction, when we're finished with this, I'll collect it. And if you have any questions, we'll go over the test. Sound good? What type of change is this going to be? Anybody know what kind of change this is going to be? Physical. Show basically talks about how nitrogen, calcium, carbon, they were made in stars. And there'll be an element periodic table that we'll examine. You'll kind of color code it, show you which stars made which elements. So what type of change do you expect this to be? Okay. Well, that was a dud. Introduce elements, and review conservation of mass. Make sure it's physical chemical change.
That are based on differences in the physical properties of the substance. For instance, a mixture of iron and sand can be separated into its components with a magnet, because a magnet will attract iron but not sand. Numerous techniques have been developed that take advantage of different physical properties in order to separate various mixtures.
Why does the sun not use up the hydrogen all at once? Anybody know why the sun doesn't use all the hydrogen all at once? Show basically talks about how nitrogen, calcium, carbon, they were made in stars. And there'll be an element periodic table that we'll examine. You'll kind of color code it, show you which stars made which elements. The current size of our sun, this little bitty dot right here, eventually it's going to become a red giant, become 2 AU as far as the unit associated with the diameter, and it will swallow Mercury, Venus, and the Earth. Hydrogen fusion reaction is the reason why the sun doesn't burn all up at once. This H2 right here is not very abundant in the sun. H2 is an isotope, and if you look at the abundance of hydrogen isotopes, it's very little of it. H3, there's even less of this. You typically don't take 4 hydrogen 1 atoms and make helium. It resists fusion. There's this hydrogen reaction cycle it has to go through, and that protects the sun from just burning up all at once, right? This big flame out, everybody freaking out. What happened? So H1 does not like to fuse to itself. Like H1 plus H1 plus H1, 4 of them, it resists fusion. Students will often sometimes think progression like baby, carbon 12, gets a neutron, turns into carbon 13, middle-aged teenager, carbon 13 grabs a neutron and becomes carbon 14. No, it doesn't do this. Because you start talking about ages, these two are stable. Close, generic close. This is a generic carbon-nitrogen cycle. Carbon 14 cycles back with the nitrogen 14. We'll get into more specifics in the chapter on radioactive decay. Now, this is another type of change.
I'll get closer because this.
Out of balloons, so I have to demonstrate something else. What type of change is this going to be?
It's going to be a physical change.
It's gonna be loud.
Sorry, it was kind of weak. But that's a physical change.